We've explained that this is how we build an inverter, although ideally this is a P-channel FET, and it's natural to ask, well, why can't I just put an N-channel FET upstairs? Would this then function as a buffer? And more generally, if we take our NAND gate, if we were to just put the N channels on top and P channels on bottom, won't we get an AND gate? It's a natural question, but this is not going to work. To understand why, we need to understand FETs in a little bit more detail, and we can do that by looking at how they're constructed. Here is an N-channel MOSFET. Our channel is right here between the source and the drain, and how deep this channel is, how many electrons can flow through it, is determined by the voltage from the gate to the body. But we have to also keep in mind that we have an N and a P region here, same here, so effectively in some sense there's a diode between the source and the body and a diode between the drain and the body. Diodes have a depletion region, and if we were to make the source a higher voltage than the body, which will reverse bias the diode, this will increase the depletion region, and the depletion region also extends in this part of the channel here. So as we increase the source voltage relative to the body, should we be separating the two? If we increase the source voltage relative to the body, then the channel here, it becomes depleted and it can't conduct as much. So as the source voltage rises, the channel is going to start to close, basically regardless of the gate to body voltage. The gate to body might be trying to open the channel, but the source to body is pinching off the channel near the source. The same thing happens near the drain. You're going to get pinch off, and then you might ask, well, how does our inverter work? Because initially the drain is going to be close to the positive supply rail. So if the drain is close to the positive supply rail, the gate increases in voltage to open up the channel. Yes, because the drain is much higher than the body, which is normally connected to the source. Because the drain's much higher than the body, there will be a pinch-off effect here, but you'll get a little bit of current flowing. And as you get a little bit of current flowing, then in the inverter circuit, that's going to decrease the voltage at the drain. That's going to reduce the depletion region, allow a bit more current to flow, which allows the drain to reduce its voltage, which allows this to open up even more. And so you see it drives it. You've got a nice positive feedback cycle here, where as the channel opens up, it becomes even easier for it to open up further, and hence the inverter works. However, if we were to set the body to 0 volts, but have the drain connected to the positive supply rail, then the channel up here will always be pinched off, and we're never going to be able to get very much current flow through here. Let's now see why this means we can't put an N-channel FET on the top of a digital logic gate circuit. Let's try the obvious thing first. Why doesn't this work? If we connect the gate to the positive supply rail, so make it a logic 1, then ideally what we want is this FET to turn on. Initially, it will start to turn on. So assuming originally the gate was 0, then the source voltage is going to be down at 0 volts initially. So if we plot here's time, here's the V out, assuming initially V out is close to 0, then we change the gate from 0 volts to 5 volts. And the FET will start to open up because the gate to source voltage has just jumped up to 5 volts. That opens up this FET here, so current is going to flow. But as current begins to flow, V out will start to increase. But as V out increases, that's the same as the voltage at the source. That means that the gate to source voltage is decreasing. The gate to source voltage is 5 volts minus the voltage here. And that's starting to turn the FET off, which means that the output will start to rise, but then it's going to stop somewhere. It's going to stop at some value far from the 5 volt value that we wanted, because to keep the FET open, we need the gate to the source to be a large voltage. As the voltage increases here, it's turning off the FET. So we're going to get to some equilibrium where the FET is neither fully on nor fully off. So this design is not going to work. The reason for the previous slide about the internals of a FET is that you might well say, okay, it's not really the gate to source voltage that determines whether this FET is on or not. It's the gate to substrate voltage. So let's be clever. Let's separate the substrate pin from the source pin and tie the substrate pin to ground. So this leads to our second attempt. In our second attempt, it's the same as before, but we're connecting the substrate to ground in the hope that if we connect the gate to 5 volts, then because we have 5 volts between gate to substrate, then this FET should be wide open. But remember what we said, there's also effectively a diode between the source and the substrate. And as the source voltage rises, we're going to be reverse biasing this diode even further, and that's going to increase the depletion region, and that's going to effectively close off the channel. So the same thing as before, as the voltage here rises, the channel gets closed off. This time it's not because the gate to source voltage is decreasing, it's because of the depletion region between the source to substrate is increasing. That causes a pinching off of the channel near the source end, but the effect is the same. That limits the amount of current that can flow, and V out is not going to get close to the 5 volts up here. So this design is not going to work either. You might then try connecting the source to 5 volts and have drain down here in desperation, but at least approximately FETs are symmetric, and so the same problem is going to occur. It doesn't matter how you try to do it, we can't have an N-channel FET at the top of our circuit and be able to have the FET in the on mode when the input is a high. So we're forced to have our N-channel FETs in the bottom half of our circuit and our P-channel FETs in the top half of the circuit, and that means we can easily make NAND and NOR gates, but we cannot easily make AND and OR gates. To make an AND gate, we actually have to make a NAND gate, and we have to make an inverter, and we connect the two together.